I think now is recording.
Yeah.
Yes. Okay. Okay. Then, good morning, everyone. Today we have Professor Vincent Vennin from LPNS Institute, Paris. The title from his seminar is Harvesting Primordial Black Hole from Stochastic Trees. Professor is an specialist in stochastic inflation with many papers in the topic and related topics. Okay, and then now, Professor, you have the word, please.
Yeah. Well, thank you very much, Giovanni, and thank you all for coming. It's really a pleasure to be invited to give this seminar, um, which is about indeed some of the work I've been doing on early universe cosmology and formation of primordial black holes, and why we need to account for quantum effects during inflation, in particular quantum diffusion, if you want to be able to predict what the abundance of those primordial black holes would be. So I prepared a few slides that I will go through, but if you have questions, don't. I know it's not easy to interrupt people on Zoom, but but please don't hesitate to do it. I would be happy to answer questions at any point, even if it means I don't have time to go through the whole slide. I think it's better if to spend time addressing questions than just rushing through the slide. So there is really no problem in stopping me at any point. Um, so my field of research is theoretical cosmology, and in particular early universe cosmology. And the way that we understand the physical processes that took place in the early universe today is that we think that cosmological structures such as galaxies and clusters of galaxies and so on, they all arose from gravitational amplification of quantum vacuum fluctuations, and that this process took place during some era that we call inflation, during which the expansion of the universe accelerated. Okay. Um, what's interesting about this paradigm is that if you apply the rules of quantum mechanics and general relativity to inflation, then what you find is that the statistics of density fluctuations, and when I say statistics, I mostly mean correlation functions in space, that depend on the microphysical properties of the fields that drove inflation. And that's interesting because it means that those statistics that we can observe, that we can measure, for instance, either on the anisotropies of the cosmic microwave background or in the density field that we probe in galaxy surveys, for instance, those observations of the statistics then they tell us something about the fields and the properties of the fields that were dominating the content of the universe at very early time. And because inflation takes place at very early time, which means at super high energy when the universe was very small and dense, it means that it gives us access to physics at scales which are extremely large. And it could be as large as 10 to the 16 GeV as far as inflation is concerned, which is, of course, many orders of magnitude above what can be probed in particle physics accelerators. And this is why we sometimes say that the early universe is a cosmological collider, which is, of course, a fancy word mostly made to receive money when we apply for funding. But there is a reality behind it, which means that it's actually a way to constrain physics at scales and in regimes which cannot be accessed otherwise, at least so far. Now, recently, there is another aspect of inflation that has become under scrutiny, which is that we might expect some primordial black holes to form. And and the physics of inflation could be related to primordial black holes. And this is one of the things that I will try to convince you of during this talk. So primordial black holes, what they are just regular black holes, but the difference is that they don't form from the gravitational collapse of a star. So the typical way we understand that black hole can form is so-called astrophysical black holes. We know that sufficiently heavy stars, when they have finished to consume all of their nuclear material, there is nothing to prevent gravitational collapse from occurring. And if the star is large enough, it might give rise to a black hole. primordial black holes are also black holes, but they form way, way before the first stars even existed. They form in the very early universe directly from gravitational collapse. Okay, so the idea is that if you produce density fluctuations during inflation, if they are large enough, they will collapse into black holes. And so of course they are a little bit exotic objects. We don't have evidence that they exist. We have some indications that they would solve some of the issues we have in cosmology, but there is no direct evidence. One of the things they would allow to solve is dark matter. So they are a very good candidate for dark matter because by definition they are dark, right? They don't emit any light. And they could also explain a number of other issues, such as, for instance, the existence of supermassive black holes in galactic nuclei. So we know that, the heaviest stars that we know, they are as big as maybe 1,000 times the mass of the sun. But in the center of galaxies, we observe black holes which are much, much heavier than that, 10 to the 6 or even 10 to the 9 times the mass of the sun. And it's a little bit difficult to understand how those black holes could be astrophysical. Of course, you can start from a black hole, which is 1,000 times the mass of the sun, and then let this black hole accrete matter, and the black hole will grow just because there is stuff falling inside of it. But if you try to model it accurately, model the astrophysics, the environmental effects, and so on, and you integrate it over the age of the universe, or say over the time you have between star formation and now, and then you realize that it's very difficult to reach this 10 to the 6, 10 to the even 10 to the 9 solar masses. So we don't really know it's not clear how supermassive black holes form, but primordial black holes, they don't have any constraints on their mass. They can form at any mass. So that might be another indication why primordial black holes may exist. Okay, there are lots of different things in cosmology or astrophysics that people take as indications in favor of primordial black holes. I don't list all of them, but I just mentioned a few. Now, as far as theoretical cosmology and early universe cosmology is concerned, primordial black holes are a challenge because they are rare. Okay, so and they are rare because they require very large fluctuations to form. So we know that typical density fluctuations in the early universe are very small in amplitude. For example, if you look at the temperature anisotropies on the cosmic microwave background, the size of the fluctuation delta T over T, where T is the temperature, is of order 10 to the minus 5. So they are very small fluctuations. Primordial black holes, they require density fluctuations of order 1. Okay, so they must be very rare. And one of the things I will try to explain is that when you deal with very rare objects, you need to go beyond perturbative techniques. And most of what we do in cosmology is based on perturbation theory, one way or the other. So this is why primordial black holes are a challenge. They require some non-perturbative techniques, and there are not so many non-perturbative techniques that we know of. So I will try to explain at least one of them, which is called stochastic inflation. And what I will show is that if you use this stochastic inflation method, you can recast the problem of finding the abundance of black holes into a mathematical problem, which is called the first passage time problem, which is essentially the problem of finding the distribution function of first passage times of a certain stochastic process. Okay, so if you imagine some Brownian motion, some stochastic process, and you look at how much time it takes for the process to hit some boundary condition, for instance, to exit your domain or whatever. And then if you try to reconstruct the distribution function associated to that time, so there are techniques available in stochastic analysis, which we will make use of. And that's exactly the problem that we'll end up having to solve. And I will say, and so I will explain how this can be related to abundance of primordial black holes. And if I have time, I will also discuss the clustering of the black holes. So how whether they in space, whether they form at random positions or whether they form into clusters, into groups of primordial black holes, which is something very important for astrophysics and cosmology. Okay, so first of all, let me insist again that black holes form into tails. So here is a very schematic picture, which actually comes from an actual model. I don't explain what the model is for the moment because that would distract me from the main argument, but I will come back to it later. I will say where this curve is coming from. So imagine that you have a way to compute the distribution function of some quantity of interest in the early universe, which I call x for the moment. I don't say what it is. But this x could be anything of cosmological relevance, such as the local curvature or the energy density. In primordial black hole, we often use this thing called the compaction function or the average compaction function. It could be anything. For instance, imagine it's the density perturbation, which is cograined at a certain scale. Okay, so imagine you have this complicated distribution function. Now, the way that we normally assess the abundance of black holes is by saying the following, that black holes, they form if the density perturbation is larger than something of order one, so you can derive some criterion when using some numerical relativistic simulations. So there is a threshold value, which is obtained, from numerical GR, for instance. And so if you want to know what is the probability for the density fluctuation to be above the threshold, well, you consider the full distribution and you just, and you just, and you just integrate the distribution above the threshold. And that will give you the probability for a certain region of space to collapse into a black hole. And therefore, that will tell you how many of those black holes you have into space. Okay, so if you have the distribution function, the problem is very simple. You just integrate it above a certain value. The problem is, of course, that it's very difficult to reconstruct the full distribution function. So what we do in practice is we design some approximations. And the best approximation we know and that people have been using for a while is called cosmological perturbation theory, where what you do is that you expand equations, and GR equations in particular, around a certain solution that we know analytically. And one such solution is the one obtained for a homogeneous and isotropic universe, Riemann-Lemaitre universe. So you decompose the metric and say the scalar field that drives inflation, which I will call phi here for simplicity, into a space-independent piece, homogeneous and isotropic piece, which is the solution of classical GR or Riemann-Lemaitre, plus a small perturbation, a small deviation away from it. So the pink terms here, they just obey classical equations. And the green terms, you can describe them as being quantum fields, okay? So of course, here is the metric. So we are quantizing the metric, but we're just quantizing perturbations of the metric, not the full metric. So it's semi-classical procedure, if you want. And what you end up with is a theory for those quantum fields, which evolve on top of background, which is given by this g mu nu bar of t. So what you have to solve is quantum field theory on a curved spacetime. If you take the full action of GR and you expand into those fields delta g mu nu, delta phi at leading order, then what you get is essentially a free theory for delta phi delta g mu nu, which admits Gaussian states. The vacuum state is Gaussian. And so if you reconstruct the distribution function of this x variable, what you obtain is a Gaussian distribution, okay, just by construction. So at leading order, you find some Gaussian. And what you can see, and we'll check that later, is that the Gaussian is very well tailored to approximate the full distribution close to its maximum. And this is, of course, something that we want, because when you look at the sky, you mostly see the most likely fluctuation. So you mostly see the realizations of x, which are around this maximum. So if you have a theory to predict the statistics of those most likely perturbations, then you're happy, okay? Of course, you can improve this picture. For instance, you can go to next to leading order in perturbation theory, so expand one more order in the action, and then you'll find some corrections to Gaussian statistics, which are sometimes described by this so-called FNL parameters, and that will improve the fit. So you see here I have a zoom around the maximum of the distribution, and the green curve, which is the one obtained from perturbation theory at higher order, gives a very good fit to the full distribution. And you can, even go to higher and higher order. What you will do is make the fit even better around the maximum of the distribution. So if you're interested in correlation functions, for instance, 2-point function, 3-point function, 4-point functions, those correlation functions, they are mostly dominated by what happens around the maximum of the distribution. So that's a very good technique. And this is why we've been using it for years and years and years to analyze the CMB data, the galaxy survey data, and so forth. Now, the problem, which you can immediately see from this plot, is that those perturbation theory methods, they give a good fit around the maximum, but they fail on the tail. Okay, they will always fail on the tail, you can show. And so if the part of the distribution that you're interested in is not the maximum, but is the far tail, which is true for primordial black holes, those methods are essentially not good enough, okay, because they will never provide a fair estimate of what happens on the tails. And so, as you know, if you're interested in objects which require large density fluctuations, such as supermassive galaxy clusters, which we seem to observe since a few years ago, or primordial black holes, or equally, super low density objects such as very large voids and so on, those perturbative techniques are not accurate enough. So you need something different. So what is this something different that you can use? So I will try to explain a little bit. The scheme that I will adopt relies on two different ingredients. One which is called separate universe, which was developed in the 90s mostly, and one which is called stochastic inflation. Okay, when mix it, which is related to the separate universe, but I will explain how they can be combined in a consistent way. So the separate universe idea, so it's a little bit technical, but I've just tried to sketch the main idea in a simple way, schematic way, is the following. So inflation proceeds very close to this de Sitter limit, where the scale factor just grows exponentially with time. Okay, so here I just wrote down the FLRW metric, where the scale factor is just exponential ht. And in this de Sitter universe, as time proceeds, a goes from 0 to plus infinity, so t goes from minus infinity to plus infinity. Now you can recast this metric in this conformal way by introducing a conformal time, eta, which is just defined by, dt equals a d eta. It's called conformal because now the metric becomes just some scale factor times Minkowski metric. And if you do the change of variable between a and eta, you find that a is now minus 1 over h eta. Okay, so during inflation, during de Sitter space-time, a goes from 0 to plus infinity, which means eta goes from minus infinity to 0 because of this expression. Now, if you draw a space-time diagram of this de Sitter space-time, so in x and eta coordinates, the asymptotic future corresponds to when eta goes to 0. So there is a line here, the blue line corresponds to eta equals 0. And the nice thing about this choice of coordinates is that null geodesics, the s squared equals 0, corresponds to d eta equals plus or minus delta x, which means that light cones is just 45-degree lines on this plot. So if you take a point in the asymptotic future and you want to draw the past light cone, it's just this very clean triangle. Okay. Now, what you can say is the following, is that if you pick up a particular time, there is a characteristic distance, which just corresponds to the distance between 2 points at that time that would just, send light rays that would meet in the asymptotic future. And this characteristic length scale is called the Hubble radius and has the following property, that if you take 2 points which are further away than the comoving Hubble radius at that time, well, if you look at their past light cones, they will always intersect because eta goes, start from minus infinity. And that's the whole point of inflation. The whole point of inflation is to solve the horizon problem. So it's that at any 2 points, they have some causal contact in the past. But if those 2 points are further away than the moving Hubble radius, they don't have any future contact. Okay, because if I place Alice here and Bob there, and Alice is sending a message towards Bob, the message will never reach Bob, even if you let time goes to, indefinitely. Okay, so there is a distance above which points do not have any future contacts. So they become completely disconnected. So what it means is that, in space now, if you consider 2 points x1 and x2, and for some reason there is some classical fluctuation which develops at x1, if the distance between x1 and x2 is larger than this Hubble radius, 1 over h, then that fluctuation cannot affect anything at x2. Okay, so x2 will never care about the fact that there was a fluctuation occurring at x1. And that gives rise to this separate universe picture in which at large scales, so at scales which are larger than the Hubble radius, you can just describe the universe by an ensemble of patches. Okay, you can just split this universe into lots of different patches, such as the one I drew here. And those patches, they are locally homogeneous and isotropic, so they are locally of the FLRW type, but they are disconnected. They are separate, okay, hence separate universe. They don't talk to each other. So what it means a little bit more technically is that you can just write down the full metric, you know, including perturbations in this way. So you see locally, it's exactly the same as that metric over there. So it's a FLRW metric, except that the scale factor is now space dependent, if you want. So within each of those patch, there is a different value of the scale factor. There is one value of the scale factor per patch. And I just rewrote this in this way, saying that the local value of the scale factor A tilde is some globally defined A times exponential 2 zeta. Zeta is called the curvature perturbation, which is a quantity of interest in cosmology. Now, if you just so this formula is also known as the delta N formalism for the following reason, which is that zeta is also the perturbation of log A, just because A tilde is A exponential zeta, so zeta is just delta of log A, and log A in cosmology is called the number of E-fold n. So we have this formula that zeta, sorry, equals delta n. Okay, so this is why this is also sometimes called the delta N formalism. And this curvature perturbation is again very important in cosmology. It's proportional to the density perturbation. It's directly proportional to the temperature anisotropy on the CMB at large scales, and so on. So if we can compute the statistics of zeta, we'll be happy. Okay. So this is where stochastic inflation comes into play. Oops, sorry, I've made it. Okay. So stochastic inflation is another idea which follows similar lines, which was proposed by Alexei Starobinsky. In fact, 40 years ago, it was in 1986, although there were some hints of the formalism in his 1982 paper. And the idea is the following. So there is this typical length scale during inflation, the Hubble radius, where we saw that above the Hubble radius, physics becomes simple because we can use a separate universe picture. So the idea is to separate things between two regimes. So there is the sub-Hubble sector, and in the sub-Hubble sector, then we have no choice but using perturbation theory because we know nothing better than that. It's not an issue because during inflation, you can show that large perturbations, they only develop after crossing the Hubble radius. Within the Hubble radius, you essentially see just vacuum fluctuations in Minkowski. It's quasi-Minkowski limit. So you don't have large perturbations. So it's okay to use perturbation theory. And for the super-Hubble sector, then we're going to use something different, which is stochastic inflation. I will explain what it is, which is non-perturbative. So this will not, at super-Hubble scale, we will never assume that the perturbations are small. We never need to do that. We'll just assume that they are large, that their spatial extent is much larger than the Hubble radius. So again, there are lots of, there are technical subtleties behind the formalism, but to summarize a little bit how it works in a schematic way, here is what you can picture. So imagine that you consider a field. So this field could be the inflaton, but it could be any other field. In fact, it does not matter. And you take this field and you Fourier expand it, okay? So you have integral over k of some phi k exponential minus ikx plus the complex conjugate. And because I want to think of it as a quantum field, I will also expand it onto ladder operators, okay? So for annihilation and creation operators. Now what I'm going to do in this field is I'm going to only keep those Fourier modes which are smaller than the Hubble radius. There is this sigma parameter here that we'll just cancel out in a minute, which means that I only keep the scales which are above the Hubble radius. So what it means in real space is that I'm just coarse graining the field. It's as if I was averaging the field against the window function, which has support over a radius, which is given by the Hubble radius, okay? So I'm just smearing the field locally, and I construct this object. Now I want to derive a theory for this object. So what can I do? So something you can do, again, schematically, is just to derive an equation of motion. And if you derive an equation of motion, so if you time differentiate this coarse-grained field, you see that you will have two contributions on the right-hand side because there are two terms here which depend on time. The first time-dependent piece is given by the mode function, phi k, because you have to differentiate phi k over time. But the point is, because you're looking at perturbations which are larger, I shouldn't say perturbations, fluctuations which have a wave number less than the Hubble radius, so they are very large scale fluctuations. Then we can use this separate universe picture. And remember that according to the separate universe picture, those fluctuations, they just obey the same equations as just homogeneous and isotropic backgrounds, which just means that you can just drop k. The effect, k becomes very small compared to the other terms in the equation of motion. So for the first term on the right-hand side, you can just use the same equations you have as for the background. Okay, so it's just the same equations as for the background in homogeneous and isotropic background here for the first term. Now, because you have introduced a time-dependent lower bound of the integral, there will be a second contribution. And the second contribution, if you look at it, will pick up modes phi k and phi k dagger, sorry, phi k ak and phi k ak dagger, which correspond to the k, which is equal to the Hubble radius. Okay, that contributes this second term, which physically means the following, that if you consider a system which is made of the scales which are above the Hubble radius, because of the expansion, the wavelengths associated to each Fourier mode grows, so they cross out the Hubble radius. So at every point in time, at every instant in time, there are new scales which join the super Hubble sector. So they add up to your coarse grain field. They kind of, they feed the coarse grain field by new degrees of freedom, which are continuously crossing the threshold. And that gives rise to this contribution. Now, something you might have noticed, although it's a little bit hidden, is that in this expression there is a hat, in this expression there is no hat. So I'm using the hat as a convention of to say that it's a quantum field. And why is it not a quantum field here? Well, this is the magic of stochastic inflation, I should say, which is that you can show in some classical limit that you can see this equation not as an equation for quantum fields anymore, but as an equation for just classical fields if you interpret this term as a random Gaussian noise, okay, as a stochastic noise. So those modes which cross out the Hubble radius, they are quantum, can correspond to quantum fluctuations. So they acquire some value, which is random. And you can just model this randomness by adding a noise to this equation. So what this equation is really telling you is that you have a local background, separate universes. Each universe is just following some local FLRW background. But the inflow of modes of quantum fluctuations throughout the coarse graining scale are sourcing these background evolutions. So the background equations are not classical and deterministic anymore, but they receive a stochastic correction. So those type of equations, they are called Langevin equation, and they just allow you to describe the field as being something that follows a stochastic process. Okay, so how can we combine all of those ingredients I've introduced and derive a scheme to compute non-perturbatively the distribution function of the curvature perturbation? Because that's my goal. So this can be done using this so-called stochastic delta Ren formalism, and it goes as follows. So imagine you have some single field inflation model, just to simplify. So inflation is driven by a single field phi. The field phi is rolling down some potential function, which here I just drew randomly, does not matter what the potential function is. There is some initial field value here. Inflation ends when the potential becomes too steep, so there is some pre-decided end of inflation point. So you start from this initial condition, and then the field follows this Langevin equation. Here I've specified the Langevin equation to a particular type of model, which is single field inflation. And there's a condition that the potential function is smooth, so we call it flat enough, we call this slow roll potential. This is what the Langevin equation looks like. I've just done it for explicitness, but it does not matter. You can also generalize it to other models. You have this Langevin equation. So what happens when you simulate realizations of the field along this potential is the following. So you see here I've just simulated two realizations. The initial condition for both is the same. It corresponds to this initial field value. And the final field value for both is also the same. It corresponds to this green spot. The thing which is different between the two realizations is the time it takes to reach the end of inflation starting from this initial condition. So I call these two values N1 and calligraphic N1, calligraphic N2. Calligraphic N is for the duration of the process. N is my time variable. N is the log of A, remember. So what it means is that, oops, sorry, I missed out something. Okay, there should be some equation here that is missing. It's okay, we'll come back to it later. So so what we'll be interested in is to try and find the distribution function associated to this time n. And this time n is called the first passage time in stochastic analysis. And first passage times, they are ubiquitous in many, many fields of physics, but not only physics, in fact, of many, many fields of science in general. The true story is that first passage times, they were first introduced by mathematicians at the very beginning of the 20th century, in particular by someone called Louis Bachelier. And they were not introduced to do physics. They were actually introduced to do finance, okay, to model stock prices and options, and trying to solve problems like if I buy stocks of something, when is the best time to sell them? When will the price hit this certain threshold where it becomes interesting to be sold, and so forth. So they were first developed in finance, but they are used in many, many fields such as nucleation theory. People studying the firing of neurons are also interested in them because it's when the action potential reaches a certain threshold in the neuron that the electric signal is triggered. So if you want to model that, you have to solve for a first passage time. Likewise, conformal changes of proteins is also relying on some first passage times. Recently, mostly because of COVID, it has been used extensively in modeling of epidemic dynamics, propagation of pandemia, and so forth. Okay, so there are lots of literature which are available about how to solve those first passage time problems. There is one thing you can say that I will just show some equations just to give you some insight that will because that will allow me to derive some at least to explain some result is the following. So if you have this Langevin equation that I wrote before, from the Langevin equation you can always derive what is called the Fokker-Planck equation. So the Fokker-Planck equation is an equation for the distribution function associated to the field value. Okay, so you say that you start from a given initial condition, and after a time n, you look for what is the field value. It's a random, it can be anywhere in the potential function, so it's a random variable, phi, which has a distribution p of phi at a given time. And that p of phi at a given time follows a partial differential equation. You see you have d over dn on the left-hand side, d over d phi on the right-hand side. And this partial differential equation is called the Fokker-Planck equation. Now, one can show that this Fokker-Planck equation is also very closely related to another equation, which is called the adjoint Fokker-Planck equation. It's adjoint in a certain sense that follows the first passage time distribution. So this PFPT here is an object that is quite different from that one over there. So here what we're interested in is say that you start from some initial condition phi, and you want to know what is the probability to exit inflation after a time n, calligraphic n. So here it's a distribution of n for a fixed initial condition, while this guy over here was a distribution of phi for a fixed duration. Okay, so they are kind of analog objects, but fairly different. But still, they follow very similar equations, which mean that you can actually derive an equation for this first passage time distribution. Now, the thing is, if you look at this equation, it looks a little bit similar to a Schrödinger equation. Remember, Schrödinger equation, d psi over dt is the Hamiltonian applied to psi, is also a partial differential equation, which is first order in time. Okay, so same for this one. And if you remember your lectures from quantum mechanics, one of the ways we have to solve the Schrödinger equation is to look for the eigenvalues of the Hamiltonian and then decompose the wave function onto the eigenstates of that Hamiltonian, and then just write down that the wave function will be those eigenstates times exponential minus I times the energy times t, okay? So here it's exactly the same thing. You can do exactly the same decomposition. The only difference is that because there is no I, in Schrödinger equation, there is an I in from d over dt. Here there is no I. So there will be no I in the exponentials. But here still will be some eigenvalues or eigenvalues of the Fokker-Planck operator. And these are eigenfunctions. Okay, the reason why I wrote the solution in that way is the following, is that if you are interested in the tail of that distribution, because of this so what is the probability to realize a very, very large value of n, because of this exponential decay, what you will have to do is to pick up the lowest eigenvalue, the lowest lambdas, which we often call lambda 0, because when n becomes very large, all the other lambdas, they will be exponentially suppressed compared to that one. So when n becomes very large, you just get some exponential decay for the distribution function. So the tails of the first passage time, they always decay exponentially, okay, which is something that that I will mention several times in the next 10 minutes or so, but that's very a crucial result. Okay, now, why am I interested in this first passage time distribution? Well, this is because n, the first passage time itself, is directly related to zeta. Okay, if I just come back to, sorry, been too far, to this slide here, remember that zeta, the curvature perturbation, is nothing but the fluctuation in the first passage time. Therefore, if I'm able to reconstruct the first passage time distribution, what I'm actually doing is directly reconstructing the distribution for the curvature perturbation. Okay? So now, why is it important that this distribution function has an exponential tail? The reason is the following. If you remember the sketch that I was showing at the very beginning, I was saying that if you use perturbation theory, only perturbation theory, at leading order, you get a Gaussian distribution. Now, a Gaussian distribution has a very suppressed tail, which decays as exponential minus zeta squared. Okay, it's just Gaussian suppression. Now we find that the tail is not suppressed as exponential minus n squared or minus zeta squared. It's rather suppressed as exponential minus n or exponential minus zeta. But that's much, much, much heavier than Gaussian suppression. Okay, so here you have a sketch, it's not a sketch, it's an actual plot, just to illustrate this statement. So this is from a paper where we computed the first passage time distribution, starting from a certain initial field value, in a potential function that was simple enough. So you see it has some linear and cubic contributions. This was because we wanted to mimic some inflection point, which are often discussed in the literature for primordial black holes. The solid lines, they are the results of the full, they are the full solutions of the John-Fokker-Planck equation, starting from different initial field values. Different colors correspond to different initial field values. And the dotted lines, they are the predictions from perturbation theory. That gives, a same kind of behavior as the one I was showing at the beginning, which tell you that, close to the maximum of the distributions, the Gaussian fits are very good. And indeed, the behavior is quasi-Gaussian. But if you go to the tail, then you see that there is a very large difference. And the difference is always in favor of the true first passage time distribution is much, much bigger. The amplitude of the probability is much, much larger. And the reason is that it decays exponentially instead of decaying as a Gaussian. Okay, for example, if you compare, this curve with this curve, you see that they are very different. This plot I've been using a log scale for the first passage time. So the fact that it goes to a straight line when n is large is exactly saying that it goes to an exponential decay. So that's really a confirmation of this exponential decay now. And the consequence of this is that now if you want to use those distributions to estimate the probability to produce primordial black holes, so you integrate those distribution functions above a certain threshold. Well, if you use the Gaussian assumption, so the Gaussian approximation, you will get a result which is vastly underestimating the abundance of black holes, just because they give you a much, much lower probability for having large curvature fluctuations. Okay, so this is what we did here. We integrated those distribution functions above the threshold for different initial field values. The dotted line is again what you obtain from Gaussian approximation, and the blue line is what you obtain using the full distribution function. And you see that, so here beta is sometimes called the math fraction, or the rescale math fraction is essentially the fraction of the universe which ends up in primordial black holes. And you see that if you use the Gaussian approximation, perturbation theory, you'll lead to the conclusion that only a tiny portion of the universe ends up in black holes, but it's vastly underestimating. There are many, many orders of magnitude between the dotted curve and the solid curve. Okay, so that's say lesson number one is that if you use perturbation theory, you underestimate the abundance of primordial black holes. What you should really do is solve for the full first passage time distribution, and then you find that the tails are much heavier. I should also say in passing that the fact that there is an exponential tail instead of a Gaussian tail is a non-perturbative thing. So you cannot describe exponential tail as being a perturbative correction to a Gaussian tail. So when you do perturbation, I said leading order in perturbation theory, you have a Gaussian, you can go to slightly higher order. If you go to a higher order, what you will get is, of course, not an exponential tail. You will get a Gaussian tail, which is modulated by some polynomial. Okay, so you will get Gaussian times 1 plus n squared and so forth. You will get some Taylor expansion around the Gaussian. But that cannot converge to exponential, never. Okay, so it's really a non-perturbative effect, and this is why I think primordial black holes are exciting because they really probe the non-perturbative regime of cosmological fluctuations. Something else I can mention is that, of course, I'm talking a lot about primordial black holes because it's kind of because they are emblematic of many issues and debates in cosmology nowadays. But actually, the tails play a role for any high density astrophysical object. And even though we've never observed primordial black holes, we don't even know if they exist. We did observe some very large density objects, which are difficult to explain using perturbation theory. One example of that, which is already a few years ago, JWST, the James Webb Telescope, has found more objects which would require a dedicated analysis. But a few years ago, there was this thing about El Gordo. So of course, I don't need to say what El Gordo means. You should rather tell me. But El Gordo is like a cluster which is extremely big, okay, extremely fat, and which was observed at redshift 0.8, and with a mass which is above 10 to the 15 solar masses. So that's extremely heavy for a cluster at this high redshift. And here I've displayed some computation of the expected abundance of clusters above 10 to the 15 solar masses per redshift bin. The blue curve, which is labeled Gaussian, corresponds to the standard lambda CDM model. So you do lambda CDM, you start from Gaussian fluctuations with a certain power spectrum with an amplitude and spectral index, which are set to match CMB measurements. And then you apply the rules of structure formation, growth of the density contrast, blah, blah, blah. You can compute what's the probability to form clusters with a mass which is more than 10 to the 15. Now, in the redshift bin where El Gordo was found, you find that there should be a few tens of those clusters, which you might say is good because we have observed one, so we do expect to find some. But what this plot does not include is the observational bias. Okay, so of course we don't observe every cluster that there is. And because this is super high redshift region, the observing bias is extremely low. So we observe only a tiny fraction of all of the clusters which exist at that redshift. And if you apply this bias, what you find is that actually the probability to observe one of those 20 or 30 clusters is extremely low. Okay, so this is why people were a little bit concerned that, why do we see this El Gordo cluster? We should not expect to see it. It's very unlikely. At least it's very unlikely. Now, the other curves which you can look at, the green and the orange one, which are labeled elliptic 2 and elliptic 4, correspond to what you find if you use the full density, the full distribution function, which includes the exponential tails. Of course, there is a little bit of model dependence in that, so it depends on the model of inflation and so on. What is the value of lambda naught, so the decay rate along the exponential. This is why here I've taken two profiles which are kind of opposite one to the other, so they are kind of two extremes, elliptic 2 and elliptic 4, just to kind of gauge what is the model dependence in this result. So, an actual model would fall somewhere between those green and orange lines. But the bottom line is that you see that at redshift 0.8, it gives a much higher abundance of those very heavy clusters. So that's good because it could explain why El Gordo was found. Of course, those kind of predictions, those kind of arguments, they are interesting only if they come with additional predictions that can be tested. Otherwise, it's too easy to post-dict something. We should also be able to predict things. And you see that there is a prediction that comes with this argument, which is that we should also find very, very heavy clusters at even higher redshift, not only at 0.8, but even at redshift above 2. Okay, so this is something that that people will probe in the future, and hopefully that will, either confirm or give some other indication for those exponential tails, or maybe disprove them. But this is something we should learn more about in the future. Okay, so I think I have something like 15 minutes left, or maybe a bit less. I will discuss clustering a little bit, and in particular trees, stochastic trees. Okay, so one issue with the formalism that I've introduced so far is that it goes as follows. So in practice, what do? We take the Langevin equation, we simulate realizations of the Langevin equation, lots of them, typically 10 millions, 100 billion. And each realization corresponds to the word line of one patch of the universe, and it ends, in one Hubble patch on the end of inflation hypersurface. So when we simulate many such realizations, we just reconstruct the curvature perturbation in all of these patches. But when you do that, you do realization by realization. So you have the value of zeta in patches, but you have no idea how those patches are located in space. You don't know how they're arranged, one with respect to the other. You don't have information about the spatial arrangement of these patches. And that's a little bit annoying because we are not only interested in how many black holes form, we are also interested in where do they form in space. And in particular, there has been some debate or there is, some interest in the last decade or so in knowing whether primordial black holes form in a clustered way, such as is depicted on the left-hand side, or whether they form randomly in space. And the reason why people are so interested in it is because it has a huge impact on the rate at which black holes merge, right? So if they form in clusters, they will merge much sooner and with a rate which is larger because they are already close one to the other. So in this picture, you would expect gravitational waves coming from early mergers, numerous early mergers, right? While according to the picture on the right-hand side, you would expect that the mergers would eventually occur, but that it would take much more time. Okay, so you would expect a weaker rate of merging. So there has been some debate about, well, if black holes form from Gaussian fluctuations of a Gaussian field, are they clustered or the non-clustered? The debate was kind of closed at the end of the 2010s, so typically 2018, 2019, in particular in this paper, where people found that, if you really use Gaussian random field, if you look at the statistics of the very high peaks of a Gaussian random field, then they are what we call Poisson distributed, so they are just distributed randomly in space. So you end up with this picture on the right-hand side. Now, the point is that, so that kind of closed the debate for a while, but the crucial assumption about this argument is that primordial black holes form from Gaussian fields. And as we saw before, it's not quite the case. So primordial black holes, they form into the very far tails, where the statistics is far from being Gaussian. It's exponential decay, not Gaussian decay. So if those are not Gaussian fields, then this argument does not apply. And legitimate question is, well, in that case, do we have, do black holes form in a clustered way or not clustered way? So that's a difficult question to answer. Let me just for the sake of time, because I want to present some things, let me just keep this slide. And that led us, when I say us, it's a number of collaborators. So Chiara Animali, who is a postdoc in Belgium at the moment, Pierre Auclair, who was first a postdoc in Belgium, who recently became a permanent in Paris, Baptiste Blachier, who is a PhD student, and Emily Thomberg, who is a postdoc, all of them in Belgium as well at the moment. We kind of came up with this stochastic tree approach to try and reconstruct the spatial arrangement of the patches. And the idea is the following. So during inflation, if you consider a patch of space, which has a size of the Hubble radius is a constant. Because of the expansion of space, if you wait for a certain amount of time, this patch will become 2 Hubble patches. Okay, so one patch becomes 2 Hubble patches. Now, if you repeat this kind of structure iteratively, that gives rise to some sort of a tree, okay, where each patch goes two Hubble patches, and then that patch goes to two Hubble patches, that one to two Hubble patches, so on and so forth. Now, what happens is the following. According to the separate universe picture, whenever a patch has become two patches, those two patches, they evolve independently, one for the other. Okay, so the Langevin equation, I don't know if you can see the numbers, maybe it's too small, but the Langevin equation that takes you from this patch to this patch, 24 to 49, they're just numbered in a round way, is statistically different from, completely independent from the Langevin realization that takes you from that patch to that patch. Okay, so this is why you see that the tree is not well balanced. It stops at different levels according to the path you follow. And the reason is just that inflation ends at different points, just depending on the Langevin realization that you consider. Okay, so you can start from some initial condition and you produce many, many patches, many, many branches. Along all of those branches, at some point, things stop just because the end of inflation is reached. And then you can reconstruct this big tree, which is just a description of your inflating spacetime. So we have developed a code which is called Forest, which produces those trees. Okay. Now, what we realize is that if you look at this tree, there is a way that you can compute not only the curvature perturbation, but in fact also the thing which is called the compaction function, which is kind of a generalization which is often used and which is thought to be more accurate to predict whether primordial black holes form. And this compaction function can be estimated just by comparing volumes which emerge from some of those patches. Okay, so by volume, I mean, for instance, if I consider this patch 18, so the volume of 18 would be defined as being the number of leaves, so final terminal points in the tree, which emerge from 18. Okay, so if I count them, there is this one, this one, this one, this one, this one, this one, this one. Okay, all of the leaves here. I've not counted them, but there are a few. And if you and that volume is very easy to estimate recursively. If you have a recursive code, you can associate a volume to each of these patches. And by comparing the volumes, you can reconstruct the compaction function, and then you can see when primordial black holes form. So you can count primordial black holes and you can locate them in space as well. The nice feature about this scheme is also that it automatically accounts for something which is called cloud in cloud. So cloud in cloud is the problem that, well, it's not a problem, but it's a mechanism by which if you've identified a region of space within which the density is large enough to form a black hole, and you declare that, well, that will add a black hole to your list of black holes that the universe contains, well, you might be making some mistake because it could be that this region you're looking at is in fact part of a much bigger region that will collapse much later, but maybe that bigger region is also above the formation threshold. And so this small black hole that you have added to your list is in fact maybe not there at the end of the day because it's just hidden within a much larger object. Okay, so that's called the cloud in cloud mechanism, and sometimes it's an issue because people don't take it into account, and that overestimates the number of small black holes. This is not an issue here because whenever we find a black hole, so here the black nodes are just correspond to black holes. This example is of course completely unrealistic because you see that most of the universe ends up in black holes, which is of course not the universe we live in, but this is for the sake of the illustration. What we do is we just keep the black hole which is the highest along the tree. Okay, so it's very easy to do when you have a chain of black nodes. We just keep the ones which is the closest to the root of the tree, and that takes care of cloud in cloud. Okay, something else we can do, but my time is almost over. I will be very quick. Is we can also create maps of the universe, but let me just keep that in fact because I don't have time. Okay, the thing let me also mention that the stochastic trees and all the mathematical problems that come with them have also been explored a lot. In particular, so you see that because of this compaction function calculation, the quantity which is important to compute is the volume that emerges from a certain node in the tree. And here is a plot of the distribution function of the volume of the trees emerging from a certain initial field value in a model that I will maybe quickly sketch later, but it does not matter. You have this parameter mu, and mu is just a parameter in the model that controls the width of the region in field space where you have a large amount of quantum diffusion. And you see that, well, when this new parameter increases, which means when the when you get close, when the size of the field space where quantum diffusion is important grows, you get closer and closer to this behavior, power law behavior, where the distribution function of the volume goes like v to the minus 3/2. And in fact, we were, surprised to see that this is something that is known, and it is known by people studying bacteria models, because actually this way of constructing trees is exactly what people do in modeling populations of bacteria. So what they usually do, and that's also important for pandemic modulations, is that you say that bacteria are quickly developing. So if you have a population of bacteria and you have traps somewhere in the box, at every time step, a bacteria can move in the box. It can either die if it meets one of those traps, if it falls into one of those traps, but it can also replicate. Okay, so that's exactly a binary tree, because at every time step the bacteria moves, either it dies or it just replicates into two bacteria, so on and so forth. And then people ask the question, and then you can wait for the entire population of bacteria to be dead, and you can ask how many bacteria in total did I produce? How many dead bacteria do I have in my box? And that's exactly the volume of the tree. So this distribution function for the volume has been computed by people doing bacteria model. It's called the Galton-Watson process in practice, in math. And they did find the same behavior. What is also interesting is the following, that some of the question that people are, of course, interested in, as far as bacteria are concerned, is whether the population gets extinct or not. Okay, so do you always have some new bacteria being born and replicating, or does the entire population of bacteria dies entirely? And actually, that is related to whether this new parameter is such that you are below this v to the minus 3 alpha or above. And this, in the language of inflation, is exactly the criterion for eternal inflation. Why? Because eternal inflation is the statement, is the regime in which there are always pockets of the universe which are inflating. So inflation does not end, never ends everywhere. There are always places in the universe where inflation takes place, which is exactly analog in the bacterium model to the question of knowing whether your population of bacteria dies entirely or whether you always have bacteria which are creating new bacteria and so forth. So there is a super nice analogy between the two things, which helped us to use some of the techniques that very clever people developed in math and bacterial modelization to inflation. Just two more plots, and then I stop. So that's just a plot of the mass distribution that we obtain in this tree. So the mass distribution of the black holes, of the primordial black holes. The only thing I want to mention is that this is a model in which perturbations are enhanced. Black holes, they form at a given mass, which corresponds to that scale. So if you have a model of inflation that enhances perturbations at a given scale, you will get what is called the monochromatic mass function. So with black holes all of the same mass. And you see it is kind of true for this blue line, but for the other ones, it's not quite true. You have mass functions which extend over several orders of magnitude. So it's kind of so this is really a stochastic feature, a feature of the stochastic trees, which is interesting. And finally, so this is just a sketch of the particular model I was telling you about. In this model, we also computed what is called the reduced correlation function. This is my last plot. Then I'm over. And this guy is just the ratio between two probabilities: the probability to find two black holes distant by r, over the square of the probability to find just a black hole at a given point. Okay, so if the black holes are just randomly positioned in space, whether you have a black hole here does not have any influence on whether you have a black hole there, and therefore the probability to have two black holes here and there are just the product of the probability to have one black hole here and also one black hole there. So this ratio here should be 1 in that case, and this 1 plus xi quantity should be 1, which you see is what we find at very large distance. This is called Poissonian statistics. Any deviation from the Poissonian statistics means that the black holes, they prefer to form in a clustered way. Okay, so it goes to 0 at low distance, but this is an exclusion effect. It's just the fact that if you already have a black hole somewhere, you cannot have another black hole. So this part is not really interesting. It does not tell you that things are not Poissonian. However, you see that there is between this exclusion regime and the Poissonian regime at very large distance, there is this intermediate regime where the reduced correlation grows to a substantial value, which means that, well, in fact, in this model, primordial black holes, they tend to form in a clustered way. Okay, so they form in two pairs of two black holes, three black holes, four black holes. So it seems that, when fluctuations are non-Gaussian, um, maybe we should consider again the possibility that black holes form clustered. Okay, this was my last slide. I just finished with a brief summary. Um, I've tried to say that, quantum fluctuations are important to predict the abundance of superdense objects, that it can be incorporated with a formalism, which is called stochastic inflation, in which you only have to solve stochastic processes, classical stochastic processes. One of the key results I've highlighted is that quantum diffusion leads to exponential tails, which are very different from Gaussian tails. They are non-perturbative feature. Um, then I've illustrated that at least I've shown how some observables can be reconstructed from first passage time analysis. I've not shown, but you can also reconstruct some other quantities of interest, such as the power spectrum and some endpoint functions and so on. I've also mentioned at the very end that not only the probability to form extreme objects, but also the way that they cluster is enhanced by quantum diffusion. And here is a question in light gray that I put in light gray because I because I didn't have time to explain, but which is essentially what do we do in the regime where eternal inflation takes place, which is the regime where the trees never end. Okay, so there are always new leaves being created in the trees. In this case, of course, it's very difficult to it's difficult to compute statistics because they are formally divergent. But we are also thinking at the moment about how we could nonetheless still define probabilities and make predictions for these regimes. Okay, I will just stop here. I can continue to share my screen, but I will just exit the presentation mode so I can see you guys because you are just hidden behind the slide. Thank you for listening.
Uh, Thank you very much, Professor, for your great seminar, and for accepting the invitation. Yes, I don't know, the students, do you have any questions?
I have a question.
Yeah.
Uh, Thank you for the seminar, Professor. I have two questions, and in fact, one is related with the eternal inflation.
Yes.
But the first, recently, in fact, I was reading one paper about the stochastic inflation about, from you, and I have a question about the fluctuation. If the fluctuation originate as oscillating quantum waves, at what exact moment do they cease to be quantum and become classical? Is only to the relationate to the crossing the horizon, or I was thinking is could be related with the quantum decoherence also?
Yes. So thank you for asking this. It's a very good question. I'm not sure I have a very good answer, but I will do my best. So indeed, so there is something which is kind of hidden in this stochastic formalism, which is that you replace, so at the end of the day, what you do is that you replace a quantum field by a random variable. And this we know is not something which is allowed in quantum mechanics in general. We cannot account for quantum correlations. All of the quantum correlations that exist cannot be described by classical correlations. There are examples of where this is not true. For instance, Bell inequalities. So Bell inequalities is a violation, is an example of some correlations which cannot be explained by just classical random fields. So when you do that, there is something that you lose necessarily. You kind of lose information about quantum correlations or entanglement or things like that. And whether or not it's a good approximation is in fact not an easy, not an easy question. Um, there are things you can do. For instance, you can compute the entanglement entropy between the patches. When you use the separate universe picture and you separate the universe into different patches, you can compute how entangled those patches are, and then what you find is that they are in fact not entangled. Okay, so that's reassuring. Um, you can also of course assume that decoherence takes place. So if decoherence takes place, that will also erase some of the phase coherence information within the patches and so on. But but indeed you need to make that you need to make that connection. One thing that I can say is that people have been using stochastic inflation, for instance, Richard Woodard and people like that, to compare predictions from full quantum field theory in regimes where they can actually compute things and stochastic inflation. And when they do that, they find that they match very well. Okay, so at least it's reassuring that we're not doing something which is completely crazy. They find a very good match. In fact, yeah, excellent match. Um, but indeed, there is always this quantum to classical transition, which is behind everything, and which which somehow is assumed to take place in stochastic inflation. In fact, it's assumed to take place everywhere in cosmology because people never, after inflation, usually people don't care about the fact that fluctuations are quantum. They just treat them as classical fluctuations. Um, so it's kind of, it's latent everywhere in cosmology, not only in this, but in everything else that we do. And I agree, it's a very interesting topic where there are many questions that are not answered. So
Thank you for the answer, Professor. And my second question, sorry for the camera, by the way, I don't have camera in my computer. My
no
second
worries.
question is related with the eternal inflation, because if the noise is random, could it push the field so hard that the inflation never ends, considering, in fact, the proportion for the eternal inflation?
Yes, yes, yes. So it could. There are different ways of defining eternal inflation, but 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 the way that I would say, that most people use is just is equivalent to saying that the probability. So if you think in terms of it's equivalent to that. If you sorry, where am I? If you think in terms of trees, you can ask if you start from a given node, what is the probability for the tree to end everywhere? Okay, if that probability is 1, then you're not in eternal inflation. That means the inflation will stop with probability 1 everywhere. If this probability is less than 1, then it's eternal inflation because it means that you will have some trees where inflation never ends. You will always have new nodes created and so forth. And that's what people call eternal inflation. Um, for us, it's not a philosophical, it's a practical thing that if the tree never ends, how do you compute statistics on the leaves if you always produce new leaves? But yeah.
Thank you, Professor. I suppose this can affect the shape of the tiles in the distribution of primordial black holes.
Yes, I think it can. I think it should have some effect. Um, what I The way that I look at it at the moment is that this eternal inflation issue is an issue because we ask the question, what is the final leaves which emerge from a given node? But this question is irrelevant from an observational point of view. It's just relevant because that's the way that we compute things. But because an observer doesn't have access to an infinite number of leaves, right? So, and we don't observe the whole universe. So I think the question we should rather ask is the following: is that an observer who is sitting on the end of inflation hypersurface, he only sees a finite region of space, so a finite region of leaves. And so only has access to a finite number of leaves. And those leaves, maybe they are part of a tree which is inflating forever somewhere else, but it does not really matter because you only see a finite number of them. So I think that somehow if we could condition the probabilities and the statistics to the fact that we that we kind of clip them to a finite portion of the whole tree, somehow I think we should be able to get finite answers. Um, but these are just words because because in practice I'm not sure how to do that. So that's that's something that I think we should work on. But at the moment it's just technically it's just when you compute things you get, for instance, you compute the mean volume expectation value of the volume, you get infinite. So it's very hard to make predictions out of those infinite numbers.
Thanks, Professor.
Yeah, thank you.
Thank you, Andres. Thank you, Professor. Any other question?
Uh, yes. Hello, Professor.
Yeah, hello.
Thank you for your seminar.
Andres.
I have a question regarding the observational point of view, as we have not yet discovered like any primordial black hole. But
Yes.
like from this separate universe approach, is there like a indirect kind of method where like we can have a prediction that like yes, from our method we can say like there's indirect evidence that the primordial black holes do exist?
Yeah, so that's right. So we don't have evidence that primordial black holes exist. Um, One of the problems is that primordial black holes are, there is the no hair theorem that tells you that from outside of a black hole, the only thing you can see is the mass of the black hole and the spin of the black hole, and this is it. And so it means that, when you see a black hole that weighs 10 times the mass of the sun, how can you say that it's primordial or not primordial? You cannot, okay? There is one thing that would provide a definite proof, definite evidence, which is if we observe a black hole with a mass which is less than 2.1 times that less than 1.4 times the mass of the sun. The reason is that stars which are lighter than the sun, they cannot collapse into black holes. They don't meet the Chandrasekhar limit. And so if we observe them, then they must be primordial. There is no other way. But those black holes are also very challenging to observe because they are small, so they don't emit lots of gravitational waves when they merge. So they would have to be very close to us if we want to observe them. So I'm not sure if that will happen soon, but maybe. Um, Other than that, it's a little bit, it's difficult to have definite evidence. But maybe in the future there will be some indirect indications. For example, if you assume that there is a population of primordial black holes, you compute the rate at which they merge, then you can predict that there should be some stochastic background of gravitational waves with some properties. If we observe a background of gravitational waves with those same properties, indirectly that will be some interesting indication, right? So yeah, so I'm not hopeless, but of course we need to be careful, right?
Yes, another question is, Professor, like I once read a paper about like supermassive black holes.
Yes,
So there they were explaining like there were some black holes, supermassive black holes that were formed very early in the universe, which was like a weird thing because they were not expected to be formed at that redshift.
yes,
So one of the method that the author was explaining is using some early massive seeds, which they said that can be produced using primordial black holes. So my
yes,
question is like, if we can predict the like when we predict the distribution of primordial black holes in the universe, can we like somehow connect it through the astrophysical observations like such as supermassive black holes? So the number of supermassive black holes or the distribution of supermassive black holes can be indirectly related to the early seeds such as the which were provided by the primordial black holes. So is that can be connected, or like is it just
yeah,
like
yeah,
a
yeah, absolutely. No, yeah. So people have been doing it. What is difficult is that you can compute the mass distribution of primordial black holes when they form. So you compute perturbations during inflation, then you know what. And this is the plots have been showing with the mass distributions. They are mass distributions at the time when black holes form. But after that, you need to evolve them until say today, and that can be done, but it's difficult because you need to model lots of different astrophysical things. Like if black hole merge, their mass increases. They also lose some of their mass through gravitational wave emission. If they accrete, then they will also grow. The accretion is difficult to model because the rate of accretion depends a lot on where the black holes are. So if they are the center of a galaxy, for instance, then they will accrete a lot. But if you want to compute the rate, you need to know exactly what's happening at the center of the galaxies, and galaxy nuclei are difficult environments to model because there are lots of non-trivial things, baryonic physics, and so forth. They should accrete dark matter as well. So I mean, yeah, so this can be done, and people have done it, but it's it relies on lots of astrophysical parameters, and which I'm not sure we understand all of them so well. But yes, but you're right. The goal is really to be able to make that connection. Yeah.
Okay, thank you, Professor.
Thank you.
Thank you, Nitesh. Thank you, Professor. Any other question? The last question?
Question, if we have time. Vanya, I don't know.
Okay.
Okay, Diego, please.
Go ahead. Don't worry. It's okay. It's okay.
Okay, so I have a question about the tails and the Langevin equation, the practical one.
Yes.
So, okay, so the drift term, the potential, it has a minus, so it pushes the field down, okay, every time.
Yes.
The other with the xi, the noise, it can push up or down, okay. So I think there is an open question about the constraints and about the noise. And when we take after the decay with the lowest eigenvalue, we kill everything, right? So then we cannot talk about how much large is the xi or not. I think it's a bit brute. I don't get the idea why we kill everything. Just take the lowest eigenvalue. Don't know if I am clear.
So I'm okay. So I'm not sure I understand, but let me see. So and when I
Okay.
say we kill everything, so this lambda naught depends on everything. It depends on the potential function. It depends on h. It depends on the amplitude of the noise. It's a quantity that depends on. I've not dropped the drift or I've not dropped the noise. What I've been dropping is I just say, mathematically, this equation, because it's a partial differential equation with first order derivatives in time, you can just solve it by expanding into some exponential functions, where the lambdas here, they are eigenvalues of that operator. But again, that operator contains the potential function, the amplitude of the noise, and so forth. When I say that I was dropping things, I was just referring to the fact that imagine that you order those lambda n in increasing order. Okay, so there's lambda naught, lambda 1 is bigger than lambda naught, lambda 2 is bigger than lambda 1, and so forth. Now, if n becomes very large, all of these exponentials, they will decay, but the one that will decay the slowest is the one
Less.
with lambda naught. Yes. So there is a point where if n is super large, you just see the lambda naught term. And what I was trying to say is that, well, once you have reached this regime, then the distribution function just decays exponentially because you're just left with the lowest lambda naught, which is something which is
Okay,
confirmed numerically, like there is this exponential decay. Yeah.
okay, so from the Langevin to the Fourier-Planck, okay, where is exactly is the noise now?
So here, the drift is here, noise is there.
Okay, and after?
The drift is here, and the noise, this is the square of this h over 2 pi. So this is, yeah, that's the noise amplitude.
So, right, inside the P, the function, the P is the noise, no?
So P is the distribution function, and it obeys this differential equation, which have some coefficients. I mean, some coefficients. And those coefficients, they are given by the drift and the noise, respectively.
Yeah, I don't get it now, but I
Okay.
don't get the xi in the Fourier-Planck equation has become to what?
No, sorry. So the xi is just a random noise. So it's a random variable that takes values, -1, 1.2. So it just takes some random values. So this is why you have some stochastic realizations here. And here there is no xi because that's an equation for the distribution function of phi. Okay, so this equation is not stochastic, it's just a classical equation if you want. It tells you how the distribution function changes over time. So what it says is the following: you take this Langevin equation and you simulate it an infinite number of times. If you simulate it of course you cannot do that in practice, but if you were able to simulate it an infinite number of times and compute the distribution, the histogram of the values of phi after some time, you will get some distribution function. That distribution function would follow this equation on the right hand side. Yeah, I'm sorry, I'm not sure it really answers your question, but we can maybe talk more offline. Yeah.
Yeah. Thank you very much.
Yeah.
Thank you, Orestes, Professor. Last question, I think, Diego Navier?
Yeah, me.
Yeah.
Okay, so thank you, Vincent, for the talk. It was really insightful. So I had a question about the code, about forest, I think it was called. So I was wondering, what are the inputs you need to run like a simulation? You need like the inflationary potential and the inflationary like parameters of the given model, and like that's all you need to run a simulation.
Yes.
Is there anything else you need to input to do?
No. It's that's all you need. You just need essentially you need the potential, and that's all. If you give me your potential function, then yeah, this is the only input. And then
Okay,
sorry, please go ahead.
so could you maybe use this code to explore, for example, a initial conditions that deviates from the standard slow roll attractor, for example, maybe?
Yes. Yeah. This is something we have done as well. So you can of course, in that case, the Langevin equation becomes not the one I showed, which assumed slow roll. So in that case, you have an equation for phi, but you also have a Langevin equation for the momentum of phi. So you have, in fact, two coupled Langevin equations. But so that's a little bit similar to what you would have in multi-field inflation, for instance. But that's okay. You can put as many Langevin equations you want. It's the code will still work. Yeah.
And uh, so I wanted to ask if this code is public available, just
Yes.
to play with
Yes.
it. So
Yeah. So yeah, I can. Yeah, it's publicly available. If you just look up, I don't have the link right now, but if you look at if you put my name on archive or Inspire, you just look at this forest paper, and within the paper there is a link to the code.
thank you.
If you don't
Great.
find it, just please send me an email, and I will send the
Okay, thank you.
GitHub. Yeah.
Nice.
Uh, Thank you, Diego. Thank you, Professor Vincent.
Thank you.
Yes, this was a very nice seminar, okay, and also I think the questions were very good also. And then yes, we are happy, no, very happy, no, about that. And also, yes, Professor, I want not to invite you also to the Congress that I was speaking to you, no, in Congress in October, okay, this year, okay. And then I
Thank you
hope
very
no,
much.
you can participate and you can come here.
Yes.
We are
Yeah. I
going to
would
be very
be.
happy.
I will also be very glad to do it and to meet you guys in person, which is always nicer than behind the screen, right? Sure. Yeah. Thank you for the invitation and for coming and for asking
Eh,
questions.
okay, thank you, Professor. We have some music now. I don't know if you are listening,
No,
but
no, no. I don't hear anything.
okay. Okay, now then we can close we can end no the seminar today. Okay, then thank you very much for all. Now we have another seminar. Okay, I'm going to send to you the email. Okay, with the information, okay? And now 15, okay? Okay, thank you very much. Then see you. Thank you, Professor.
Goodbye,
Professor.
everyone.
Bye
Very
bye.
much.
Thank
Bye,
you.
everyone.
Bye.
Thank you.